We have a photoelectric effect question 10 and question. Sorry, I didn't greet. I'm being quite rude here. Hello, good morning or good day, whatever time of the day you are. Okay, I'm sorry. I was just too eager to get into this question. So we have a question 10 in a Free State September or trial paper or prelim paper in September 2022. And this is a photoelectric effect question. It normally comes as a question 10 question in our physical science or paper 1 paper, or it can come as a question 11 question if the Department of Education is feeling a bit nasty. This was downloaded from stanmorephysics.com. It's a website that you can use to get a lot of different past papers, especially the grade 12 library is quite extensive and they update it quite frequently. It's not sponsored. If they do sponsor, and I hope they sponsor me, I need the money. So let's break down this question. Whenever you see a photoelectric effect question, it can only come in one of two ways, where they are either giving you raw values for you to be able to substitute into your formula, or they give you a graph and then you'll be able to identify what the different points in the graph mean and solve the questions accordingly. This is obviously the latter of the two. This is a graph type question. Before we get there, we need to go over a very important concept in photoelectric effect, which is breaking down this formula. If we want to break down this formula, we know that the main formula for photoelectric effect is the energy of the incident light. E, energy of the incident light, is equal to the work function of the metal plus the kinetic energy or the maximum kinetic energy of the photoelectron. We have to know what each thing in this formula represents. As I said before, this is for the light, for the incident light. This is for the metal. And this is for the photoelectron. So it's quite important, imperative, integral, any synonym that you can come up with to know the breakdown of this formula. Why? Because when you are given questions or you are given a graph like we have been here, you'll be able to take the information that you're given and put it or allocate it in the correct place. You'd know that, okay, this piece of information, this frequency that I've been given, this belongs to the metal. Or this frequency that I've been given belongs to the incident light. Or this velocity that I've been given belongs to the photoelectron. It belongs to EK max. If I'm talking about, for example, incident light being just equal to our work function, then you'd know, look, there's no EK max, so on and so forth. That's why it's so important to know this skill, of being able to allocate it into the different sections of this formula. Now, let's start with the question. Enough rambling. Different frequencies of light are shown onto the surface of a metal cathode of a photoelectric cell. The fact that they use the word different entails that some of them might reach the required amount of energy or frequency to cause the photoelectric effect to happen, and some of them will, some of them might not, some of them might. It then says that the graph below shows the relationship between the maximum kinetic energy of the photoelectrons, which is what we were talking about before. Kinetic energy is only for photoelectrons, and the frequency of the incident light. It's very important that they use that qualifier to tell you that this frequency is about the incident light. After this, we need to know what the different points on this graph mean. We have three very important points in this graph, as well as what the gradient of the graph entails. And we're going to talk about all of this now. So let's label the points on this graph as A, B, and C. So what does A stand for in this graph? A stands for our work function. You guys know all of these definitions. I hope you do. If you don't, please go over it. There's no blame on you, but you should go over it, please. A work function, the minimum amount of energy needed to eject an electron from the surface of a metal. And B is going to be our threshold frequency. I hope to God that I'm spelling this correctly, because I don't know, it just doesn't look Correct. So threshold frequency, the minimum amount or the minimum frequency needed to cause an electron to eject from the surface of a metal. And then C is just a coordinate or point where X is going to be the energy of the photoelectron, because that's our X value. And Y is something that we know, 110 times 10 to the 14, because it's times 10 to the 14 hertz, which is the frequency of the light being shown onto the metal. Now, it's important to know all of these points, what these points mean. Please, if you don't understand it, I know this is not what teachers say, but commit it to memory. Just commit it to memory. It will help you a long way so that you don't spend a lot of time thinking and trying to make sense of things that maybe you don't understand or you don't want to understand. Then next, our gradient. What is the gradient? The gradient of this graph is Planck's constant, or H. We know that H, or Planck's constant, is equal to 6.63 times 10 to the negative 34. Now, let's start solving the questions at hand. The first question is a definition type question, and it says to define the term work function in words. We know that these definition type questions are normally, especially in photoelectric effect, they're normally like reflections of one another. They're quite similar. And that's the same case here. If we want to define work function, it has to do with the energy required. So our answer would be as follows. 10.1. We would say it is the minimum energy required. You can use required, you can use needed for a photoelectron to be ejected. You can use removed, you can use released. You can see I'm quite good with my synonyms. Released from the surface of a metal. Now the key phrases over here are obviously going to be minimum energy. And then after that, ejected, removed from the surface of a metal. You have those two key words. If you have them there, however you want to put it, you are laughing to the bank, and then you get 2 marks. You get 2 marks unless the marker doesn't like you. Then, or it's not able to read your writing. Then you get 0. Obviously, I hope that doesn't happen. 10.2. It says give a reason why no photoelectrons are released when light of 45 times 10 to the 14 hertz is used. So we talked about this, and there is an analogy that we can use for this in terms of maybe suitability for a job or something like that. But I'm not going to get into the analogies. I'm just going to break it down into 3 different types of scenarios. It is either the frequency of your light, and I'm going to say the frequency of the light is equal to FL. It is equal, the frequency of your light is less than the required frequency or the threshold frequency, or the frequency of your light is equal to the threshold frequency, or the frequency of the light is more than the threshold frequency. So it's either one of these 3 things. It can only be one of these 3 things. So the results from these 3 things obviously result in different scenarios for our formula and different scenarios for the whole situation. Now, if your required frequency is more than your frequency of your light, then there will be no photoelectric effect. If the frequency of your light is equal to the required frequency, then there is going to be the photoelectric effect, but there will be no extra energy left for the photoelectron to move. So there will be no EK max. It will just be released, but it might not move as far as required. The last scenario is if your frequency of your light is more than required, here there would be a photoelectric effect as well as some energy left over for EK max. So those are the three scenarios. We can see from the question, we talked about the different things in a graph symbolizing different things. So this point over here that we coined or termed as point B, we said that point B is the work function. So it's the threshold frequency or cutoff frequency. That's also another word we use. And we can see that the light, 45, is less than 50. You're in grade 12. I'm sure you can handle that. We know that 45 is less than 50. Sometimes you might need to pay attention to the exponents here. If I was an examiner, I would use this. Maybe I would say 45 times 10 to the 16, and then it might trick people. But pay attention to that. But we know that 45 is less than 50. And so our parents paid enough school fees for us to know that. So we can say that that fits into the first category. And so to write a reason for our answer, we can say that no photoelectrons will be released. So we can say since 45 times 10 to the 14 hertz is less than the cutoff frequency. And you can use the therefore, want to sound a bit fancy for your marker. Therefore, no photoelectrons will be released. Right, let's move on to the next questions, 10.3. Which quantity can be determined from the gradient of the graph? We already talked about this. This is old news. We say if you know what to expect, if you know the breakdown of the graph, this is already old news, man. So we say that the gradient of the graph, it is Planck's constant. The quantity that can be determined from the gradient of the graph is Planck's constant. Or you can put the term H to support what you're saying as well. Let's move on from this. If you do want the proof for that, it's quite simple to know what the proof is. We know that if you want to find a gradient, it is the change in y over the change in x. And since we look at our graph, we can see that our y value is energy, so work, and our x value is frequency. And if we look at the formula WH times F, if I put W over F, I will get H. If I put Y over X, I will get M. So you can think of it like that. Then it asks us to calculate the magnitude of X. We talked previously about what X is. X is in point A, and we said that point A is the work function. So it wants us to find out the work function. What formula do we use to find out the work function or work in general when we talk about the photoelectric effect? Work is equal to Planck's constant times frequency. And to be more specific to the situation that we're dealing with, work function is equal to the Planck's constant times the cutoff frequency. So let's substitute the values associated with this specific formula. Well, we know that this is X, since we want to find out what that is. And H would be 6.63 times 10 to the negative 34. Multiplied by the cutoff frequency, which I believe is 50 times 10 to the 14 hertz. Now from this, you're going to get your final answer. And I'm going to say hopefully you get your final answer. Because frankly, some people, and I don't know if the thumbs are too big or maybe you've been bewitched, because some people put the exact same figures that I put in my calculator, but we get different answers. And most of the time, they get different answers. They get the wrong answer because I'm never wrong, obviously. So I don't know if you've been bewitched or your thumbs are too big to press the buttons on your Casio calculator, whatever calculator you have, please be careful. You know that when you write in exams, you even put the 2 plus 2. You put 2 plus 2 in your calculator. Please be careful with this, guys. We don't want to lose one useless, stupid mark, and then you get 2 out of 3 here. We don't need that. So when you put that in your calculator, you're going to get 3.315 times 10 to the negative 18 joules. Don't forget the joules. We are talking about work. So that is the value of x. That is the value of our work function. Now, let's move on to the last question and its sub-questions. It says that we have light of a frequency of 110 times 10 to the 14 hertz shown onto the metal cathode. So this is the frequency of the light being shown. Remember, we said the formula that we are dealing with in photoelectric effect, E is equal to work function times EK max. And this is what I was talking about at the beginning of the video. Where does this 110 fit in? Does it fit in here? Does it fit in here? Or does it fit in here? Well, obviously it doesn't fit in with EK max because EK max has to do with the photoelectron. Here we are talking about light of a frequency. It does not fit in here as well because WO has to do with the metal, but we are talking about light. E over here is talking about light, so that's the information that we've been given. We know that this E can be expanded into this E can be expanded into E is equal to H times F, and so we're gonna substitute that 110 over here into this expanded formula. It then says we must calculate the speed of the ejected electrons. So they want something here. This is what is required. That would mean that we have information here and here. We talked about what we're going to do here. We're going to say H times 110. Here, we know what the work function is from the previous question. Please, guys, you need to know that you're going to use previous questions to solve the current question that you're dealing with. Don't be negligent of that fact. So this is going to be over here. Then you're going to open up this half times m times v squared, and then you're going to solve this, and then you're going to go home happy because this is the final question of the paper, and you get out there with something. You say, I'm leaving here with something, even if you failed every other question in your paper, and I pray to God to save you guys from that. At least you can say, look, I aced that photoelectric effect question. Let's do the substitution. Enough rambling from me. I can do that sometimes. So we're going to expand this H times F. And over here, we know what the value of this is from the previous question, 3.315 times 10 to the 18. And I'm also going to expand this over here, half. And remember, we are talking about a photoelectron, which is an electron. So you want to get the mass of an electron. The mass of an electron is 9.11 times 10 to the negative 31 kg. Let me see. Yes, it is 9.11 times 10 to the negative 31 kg. And then this is multiplied by the velocity. And that's what we want to find. We want to find what is the velocity. Remember, it is squared. So we're going to have to take the square root after. Let's open this even more. 6.63 times 10 to the negative 34 multiplied by 110 times 10 to the 14 is equal to, let's just put this on this side. So I'm going to pull this on this side. Minus, it becomes minus 3.315 times 10 to the 18 half times 9.11 times 10 to the negative 31 multiplied by v squared. Now this is just my tip. And I don't want to impose anything on you. I would like to, but if you want to do it your way, you do it your way. How I would put this in a calculator is like this. I'll put it exactly like this. 10 times negative 34 multiplied by 110 times 10 to the 14 minus 3.315 times 10 to the negative 18. And then we put this all over because you have to divide it by that half. Half times 9.11 times 10 to the negative 31. And then obviously we are going to take the square root of both sides. So this is how I would put it in a calculator. Obviously I don't want to impose, I want to impose it on you, But the way you do it is the way you do it, guys. Really, I have no control over that. So 2.955 times 10 to the 6 is the answer that you get. Don't forget your units, meters per second. So this is how you solve this question. 4 marks given to you for free. This all stems from the fact of knowing what each part in the formula stands for and what the information I've been given, where does it fit into this formula. Now let's move on. So that was 10.5.1. We want to move on to 10.5.2, which is probably a relationship question. Yes, I'm right. I'm always right. What effect will an increase in the intensity of the light have on the maximum speed of the ejected electrons? So, we're talking about the intensity of the light. So this is just a theory-based question, and I'm going to give you the theory on this. I'm going to do more questions on photoelectric effects, so we'll talk about more theory the more questions that we do. Intensity of light. This only affects the number of photoelectrons per unit or whatever. It affects the number of photoelectrons, which in turn, if I have more photoelectrons, then I'm going to have more current. So if I increase my intensity, I will increase the number of my photoelectrons and I will increase my current. Because current, if I remember, I don't quite remember the formula. I think it's charge over time. Yeah, I think it's charge over time. So if you have more photoelectrons, more negatively charged things, your charge is obviously more, and so your current will increase. So intensity, just to brief what I'm trying to say, or summarize what I'm trying to say, intensity affects current, or intensity affects the photoelectrons. It does not have a effect on the maximum speed of ejected electrons. The only way that you affect the speed of photoelectrons is if you increase the frequency of your incident light. Remember what we talked about before. We said if the frequency of my incident light is more than my required frequency, I'm going to have PE and EK max. So if you can compare two, so I have one light that has more than my required frequency, then I have another one that is even bigger than the previous one. Obviously, I'll have a lot more left for my EK max. Let me give a tangible example for this. So we have 5 hertz, let's say 5 hertz, and the required to be able to cause a photoelectron to be emitted is 3 hertz. I will have 2 hertz left, 2 hertz of frequency left, and this will all be taken by EK max. So this will obviously affect the speed at which my photoelectron moves. But if I increase, now say for example I use a light of 7 hertz, and again the required is 3 hertz, I will have 4 hertz left, and this 4 hertz left will be converted or used for EK max to move this photoelectron. Now I ask you again, which one is faster? You're gonna say obviously this one is faster because I used a higher incident frequency, or a higher incident frequency. That's why I had a lot more left for EK max. Intensity doesn't affect this, so we tell them, hey Buddha, stop lying to us, it stays the same. So your answer is gonna be stays the same. And we say the reason why we stays the same is that example or that explanation that I gave on top of here. You say intensity does not affect the speed of a photoelectron, rather it affects the number of photoelectrons, which in turn affects the current according to I is equal to Q over T. Or you can just say intensity does not affect the speed of photoelectrons, it only affects the number of photoelectrons per unit time or per unit whatever. I don't know what it's per. I'm sure it's per unit time because of this formula. So that's the answer. Stays the same, you get 1 mark. Then your reasoning, it doesn't affect speed, it affects the number of photoelectrons, you get 2 marks. You are laughing out of the examination room if they allow you to do so. I hope this was of help to you. I don't know how long this video was. I'll put a snippet of it somewhere, and then the rest of the video, if it's too long, will be on YouTube. Follow my YouTube channel, man. Share, spread the news. If you get something good, share it with the people that you value and care about. Share this video to someone who needs it as well. I hope this was good for you. Bye.